Question 1. Can you dissect a square into two equal area triangles? If you answered no, just click off the video, man. Question 2. Can you dissect a square into 22 equal area triangles? Well, just repeat the procedure from before, and it becomes obvious that you can partition a square into any even number of equal area triangles. Question 3. Can you dissect a square into 5 equal area triangles? If you answered yes, are you stupid or something? Didn't you read the title? Monsky's theorem states that a square cannot be divided into an odd number of overlapping triangles, all of the same area. For example, look at this picture that I stole off of Wikipedia. Although you might believe that these are 5 equal area triangles, I wouldn't believe that, because I counted each individual pixel in the image. Only one proof of Monsky's theorem is known, and it combines Sperner's lemma, p-adic valuations, and Chevalier's theorem, 3 techniques wholly unrelated to geometry. Take a polygon, split into a bunch of triangles, then color each triangle's vertices with one of 3 colors. Call them 1, 2, and 3. We'll call a triangle complete if each of the 3 colors appear as a color of one of the triangle's vertices. We'll call an edge a 1, 2 edge if, it's not that hard to guess, as a 1, 2 edge if it connects a 1 color vertex with a 2 color vertex. Sperner's lemma tells us that the number of complete triangles is equal to the number of 1, 2 edges along the polygon's boundary. Okay, and now on to a wholly unrelated topic. Notice, or blindly believe me when I say, that all rational numbers can be written in the form of 2 to the n times a over b, where a and b are odd integers. The p-adic valuation of a rational number is defined as that value n, except for 0, where we just define its p-adic valuation as infinity. Then, the p-adic absolute value of a rational number is 2 to the power of negative v of x, where v of x denotes the p-adic valuation of x. Intuitively, this means that a rational number divisible by a really large power of 2 will have a really small p-adic absolute value. As an absolute value, specifically a non-Archimedean absolute value, it comes with a lot of important properties, but most of them aren't important. What you should really make sure to remember as we go into the proof, however, is that the p-adic absolute value of a number is less than 1 if and only if that number is even. Chevalier's theorem on extensions of valuations is how we go from dealing with p-adic nonsense on the rational numbers to p-adic nonsense on the real numbers, in order to apply them to our square. How do you prove his theorem? I don't feel like telling you. Just take on faith that it's possible to apply p-adic nonsense to real numbers, or go to Google. So, now we have all 3 pieces of the puzzle. A p-adic absolute value, a way of extending it to the real plane, and a weird thing with coloring vertices of polygon. Now what? Let's separate the points of the plane into 3 groups based on their p-adic absolute value, or more specifically, a special extension of our p-adic absolute value using Chevalier's result. If we form a complete triangle by choosing a point from each of these 3 groups, then Monsky argues that I'll have an area with a special p-adic absolute value that's greater than 1, which he shows with like a determinant or something. Let's assume that our square is the space contained by 0 to 1 on the x-axis and 0 to 1 on the y-axis. Imagine that we've successfully divided our square into m triangles of equal area with vertices colored according to their positions corresponding group. We want to show that m must be an even number. We can only draw 1, 2 edges on the line from 0, 0 to 1, 0, as we can't have a 2 color from 0, 0 to 0, 1, and we can't have a 1 color from 1, 0 to 1, 1, or 0, 1 to 1, 1. Furthermore, not only do we know that there isn't a 3 color from 0, 0 to 1, 0, but we know 0, 0 is color 1, and 1, 0 is color 2. Then, Sperner's lemma tells us that we must have a complete triangle somewhere in the triangulation of our square. We also know from earlier that it's a p-adic area that's greater than 1, but we also know that the area of a square is m times a equals 1, so m must be less than 1. But what did I tell you to really make sure to remember? Wrong, you suck. It's that the p-adic absolute value of a number is less than the 1 if and only if that number is even. So we conclude that m is even, which means that you can't dissect a square into an odd number of equal area triangles. You may be asking, why is it important to know this? Remember to like and subscribe.